Honors Physics kids. This video is to follow up a little bit on diffraction, and we'll talk about some of the mechanics of diffraction. Then I want to introduce you to something new today, another wave behavior called resonance. So with our last video, we talked about diffraction, and what we said diffraction was the ability of a wave to pass around a small barrier or through a small opening. So if I send these straight waves like this, and we define these, I think we talked about them last time as wave fronts. And so then this is the peak of the wave. So if I were to look at, this is looking down at the top of the wave. If I looked at the wave from the side, there'd be a peak, a peak, and a peak. So these fronts should line up at the top. So again, those are the wave fronts. This is what we call the ray line. So again, that's an imaginary line. You can't actually see that. It's just showing the direction of travel. But as these wave fronts approach a small opening like this, when they get to the other side of the small opening, they spread out into that region. And they go from straight wave fronts to circular wave fronts like that. And so now the rays, you could draw several of them, showing that it's spreading out like that. Okay, so that's diffraction. Again, the other type of diffraction is when we have a little tiny barrier here, and then it wraps around slowly and eventually reforms the straight wave fronts. Not my best picture, but that was diffraction. So the question is, why does this happen? And it took a little while for scientists to figure this out, because this is a fairly easy behavior to recognize. I know the way I learned it was with what was called wave tanks, and so we had a little tank of water, and we used a paddle to hit the water a few times to try to create these straight wave fronts. They'd approach along, we'd put little kind of like dams in there, and we'd see this perfect little effect. So pretty easy experiment to do, but why does it happen? Well, here's the trick to it. If you take that same tank of water, so I got this big old tank of water like this, and I drop a single drop of water in that tank, what's it do? Well, what we know is it creates these circular wave fronts that spread out away from that source. They start to head out in every different direction like this, circular. And the reason why they make perfect circles is because this medium is water. And what we know about wave velocity is wave velocity depends on the medium itself, and since it's water in every different direction, and you have to assume that my water is equal depth in every different direction, and it's equal temperature and pressure, and everything's the same about the water. It means if it's the same velocity, so every wave traveling this direction is traveling with the same velocity in this direction, same velocity in this direction, same velocity in this direction, but for the same amount of time, we'll travel the same distance, and that's a circle, right? So we get circular wave fronts. So a point source like this, point source gives us circular wave fronts. Now, what's that have to do with anything? Well, if you take a look at this, you see how there's kind of some circular look to it? This certainly has a lot of circular look to it. And that's what this person named Huygens had figured out. And so we get this idea called Huygens principle. I hope I'm saying his name right, because it's not like it's in the classroom where it just disappears. This is recorded forever, right? So, Huygens principle. And what Huygens principle says, in effect, is it says that a straight wavefront is composed of many circular waves. Now, there's more to Huygens principle. There's a lot of math to it, but this is the piece that we need to understand diffraction. And it's pretty simple. Straight wavefront is composed of many circular wavefronts. How does that help? Well, let's think about this. Instead of having a single point source like that dot, which makes a circle around it, if we put a bunch of these dots really close together, and we start drawing circles around each of them, if we make these dots even closer and closer together, you see the front of these dots almost forms a straight line. And so that means if we disturb all of these points of water or whatever it is, air, whatever medium the wave's traveling through at the exact same time, they create circular disturbances, which if the particles are close together, has the look of a straight wave. And so that disturbs the next set of points. Let me draw that in a different color maybe. So the next set of points are along this line. They get disturbed. And so we get another wavefront. And so that continues to propagate through the space. And so these straight waves are composed of circular waves. And so on. So this waves traveling in that direction. Right, so we have these straight wavefronts like that. They didn't mean to spread them out further. That would show the velocity was changing. But so how does Huygens' principle explain diffraction? Well, let's think about that for a second. If we place a barrier right here, so now those water waves can't be disturbed because there's no water there. There's a piece of wood or metal or something like that. But right here in the center, there is a dot of water that can be disturbed. So again, each of these are disturbing away. Now when we get to here, this is going to disturb a circular wave in front of it, which now disturbs other circles, which disturbs other circles. And you see how the wave front has changed shapes now because there was no other dots on either side of it disturbed because the barrier is in the way. And we start to make these circular wave fronts and spread out. And so that's Huygens' principle. Now, I tried to find something for you that might be a better visualization of my drawing here. And so, let's see, we've got from Wikipedia, they had a pretty good little picture here. And so Wikipedia is showing these straight wavefronts coming in. They're showing these yellow dots as being the circles. And so that's what I was trying to draw, right? So that yellow dot is the source of these circles traveling out. This yellow dot is the source of these circles traveling out. And you see we get this shape. Now this looks a little different than mine because the barrier is wider open. And so that's an important detail. This spacing here that goes from here to here, that spacing is showing that a bunch of different point sources can make it through. So see how it's relatively straight in the center, and the edges get the curling. If we imagine shrinking this down, we're going to get a little bit less of that. Now they've also have a little animation here that's showing that. Here's the straight wavefronts coming in, creating that circular wave. So that single point source spreading out like that. And so again, that's Huygens' principle. Now, if I try to draw that effect that we saw with the bigger spacing, so what I'll do is let me draw a really small opening here for this one, and for this one I'll draw kind of a bigger opening like that. And I'll send the waves in, so I'll try to have similar wavelength waves here. Okay, so here's our waves coming in this direction to these two different openings. Well, this is going to create circular waves. They're going to spread out and be mostly circular and spread out and cover most of the space. Now this one is going to have a little bit less, mostly straight, a little bit of curve. A little bit of curve, mostly straight, a little bit of curve. Spread out like that. Again, didn't do a perfect job because the wavelength here should equal the wavelength there, but I accidentally made that a little bit bigger. So hopefully your drawing's better than my drawing. So when we look at the spacing here, this value that maybe we could call D, when D is less than the wavelength, we get these more circular fronts. When D is greater than the wavelength, we start to get a lot more straight fronts. Okay, so D again is the spacing in here. Okay, so Huygens' principle explains why diffraction occurs. The fact that every one of these straight waves, although they look straight, are really just lots and lots of little circular wave fronts. There's some cool math that goes along with it that'll help us a little bit later on when we talk about this process called double slit diffraction, where we'll have two slits like this, and then we'll let these waves interfere with each other and create a cool pattern. So Huygens' principle. So the new wave behavior for today, I don't know what wave behavior number we're up to. Maybe we're up to 8 or something like that. I've been putting numbers on them. But another wave behavior is this thing called resonance. I have to look at my cheat sheet here to see if I spelled it right. No, I didn't, because there's no U in there. Resonance. Sorry about that. So let me go to full screen here. So resonance. So to explain resonance, we have to talk about a couple different ideas first. And so the first little bit of this is called something called natural frequency. So a natural frequency is to say that all objects, and literally the word all, so remember what frequency means. Frequency is the number of oscillations per second. So everything, so this red marker that's sitting here in front of me is shaking right now. Can't really see it. If we could zoom in a lot, we could see it shaking. All those little molecules in it are oscillating back and forth. And all objects vibrate at a frequency that depends on its physical makeup. Now what I mean by physical makeup is that has to do with what it's composed of, meaning the materials that it's made of, but it also has to do with its geometry. So this Sharpie marker has a certain frequency because of the materials it's made of, because of the plastics and the ink and everything else that's involved in it, but also the physical makeup. And so that means if I make a change, so if I take the cap off my marker, it's going to have a different natural frequency now because I've changed it physically in some way. If I were to cut part of it, I'd change it. If I filled it up with more ink or took more ink out, any sort of change at all to its physical makeup, which again has to do with its geometry and what it's actually made of, any change at all will change this natural frequency. So that means everything just kind of oscillates a little bit. Now the easiest way for me to prove that to you if we were in the classroom would be with a tuning fork. Because a tuning fork is going to oscillate at a natural frequency that's audible, so meaning that our human ears can detect it. So when this tuning fork shakes back and forth, and it's going to be really hard for me to show shaking, but we just say that it's moving back and forth like that, shaking, it's going to bump into the air, and that air is going to get compressed or decompressed depending on if it's oscillating in this direction. It compresses the air. When it comes back, it decompresses the air and compresses as it shakes back and forth like that. So that sound pulse gets to our ear and we can hear that. So if I have a tuning fork that looks like this, and then I have a different tuning fork that's maybe longer, even though it might be made of the exact same material, it's just physically longer, it's going to oscillate at a different natural frequency. And so a tuning fork just sitting here on the table, we're not going to be able to hear it, but if I bang into it, I give it a little whack to get it to oscillate, so I've upped its amplitude of its oscillations. That amplitude of oscillations will be enough to disturb the air so we can hear it. So even when we can't hear it, it's still shaking. It has some sort of energy. It's got some temperature. But if we disturb it, we can make it shake a little bit bigger, and so we can maybe see it, or in the case of the tuning forks, actually hear it. So that's the first bit of resonance. Everything oscillates at its own natural frequency, which depends on the physical makeup. So what's resonance? Well, resonance occurs when you hit an object at the same frequency as its natural frequency. An object is struck, sorry, a little funny, struck by a wave that has the same frequency as its natural frequency. And there's a lot to that. What that means is this. If I send this wave in, like this, here's the wave, it's got a certain frequency, and it strikes something like my tuning fork, that has the exact same frequency. The tuning fork, when it shakes to the right, well then when it comes back it gets hit by the next wave, which makes it shake further, gets hit by the next wave, makes it shake further, and we end up with a tuning fork that's shaking really, really large. Now, that's not true if I send some frequency in here that's not the same as the natural frequency of this, is then it wouldn't hit at the right time. So while this was shaking to the right, the wave might be pulling it back to the left, which would make the oscillation smaller. Now, the best example I have for you of that would be a swing. So here's a little kid on a swing, and here's their parent. It's going to give them a push. So when do we want to push the person on the swing? So meaning, do we want to push them when they're at the bottom of their swing, down here? Do we want to push them when they're over here? Do we want to push them back here? Somewhere in between. And the answer, for those of us that have pushed people on a swing before, which is just about all of you, is we want to give them a push right when they're at their peak here. Give them that push. If we give them a push when they're at the peak, the swing oscillation will get bigger. So if our swing was swinging back and forth like this, if we push them right over here, we can make them swing further. If we push them again, we can make them swing further. Push them again, we can make them swing further. So if we push at the correct time, we can make the swing get bigger and bigger and bigger. And so what resonance does is resonance increases the amplitude of the oscillation. So when this person swings, I push them at the right time. And if you think about it, as you're sitting there, if you've ever pushed someone on a swing, you get kind of into a rhythm. They come, you give them a little push. And you wait, and you give them a push. You wait, you give them a push. And you keep doing that over and over and over. You end up finding that you're doing it at the same time every time. So that same time is the frequency. So the more often, or not the more often you push, because that would change the frequency, but if you push, every time you add energy to them, their swing gets bigger and bigger and bigger. And since amplitude shows the energy of a wave, it increases the oscillation. And music is a great example of that. So if I take, say, a little string, pull a string really tight and pluck it, it's going to make a little twang sound, a little twang. But if I place that string on top of a box that's got a very specific size opening and I pluck it, the whole box will oscillate. And that box would be the example of the resonant chamber in, say, a guitar or a violin or something like that. So the string by itself, a little bit of sound. But if we can make that string's oscillation drive into the box and cause the whole box to oscillate, it makes that deeper, richer, longer, louder sound. So what's oscillating is not the string, but the air column inside the box itself. There's some really cool labs that we can take a look at that go along with that. So what I'm going to do is I'm going to post, I'm going to post a couple other example videos that some other people have done for you to take a look at. But our basic definition here of resonance is that we have to hit something with this exact same natural frequency. That if we do, it's going to increase the amplitude of the oscillations. If we're not at the same frequency as the natural frequency, we don't get that effect. And there's a lot of different experiments you can try at home. Have a great day, everybody. Resonance and Huygens principle. Talk to you soon.